Recording is rolling. It is Friday, May 2nd. So, as promised, we're going to Quantum Journal today. You guys remember a couple days back, I gave you guys this quarter page. You guys took 4 pages of paper, stapled them together, got titled Quantum Mechanics Journal, and then divided into quadrants and start writing these topics. I will put this together with you guys, really help you guys out here. So, I think a good structure for this last main topic that we're doing in this class is really just kind of exploratory, like what topics are involved in quantum mechanics. Right, right. So we do this. So here's my plan for next week: is I want to alternate back and forth between this and final exam review. So when I see you guys Monday, I'll open up a Kahoot. We'll do more final exam review. If we have about 10 spare minutes, we might do a little bit more of this journal, right? And then Tuesday's journal, then Wednesday, we should be wrapping up the final exam review by the end of Wednesday. And then Thursday, Friday, round out the week, possibly be wrapping up this quantum mechanics journal then, right? And then I'll see about where we are. All right, so you guys go with the agenda, what we're doing. All right, so what is quantum mechanics fundamentally? Well, the history of this goes back to about the late 19th century, so about the 1880s or so. There's starting to be this discrepancy in physics between classical mechanics and predictions and empirical measurement. But like one of the weird things that people saw. Now, I don't have a quadrant for this, but maybe I should. I don't know. I might revise in the future. Something called the ultraviolet catastrophe. So it goes like this. Scientists were working with these ovens, right? Like these black boxes, these ovens. They had a small hole in them so that light energy could enter or exit right through that small hole. And they could change the temperature. I have a curve here that's at 5,000 Kelvin, could be a specific temperature. And they could change the frequency of the light. Now, according to classical mechanics, matter can exist either as waves or as particles, and there's a distinct box categorization, right? You can exist as a wave, you have a wavelength and a frequency, or you exist as a particle, some discrete like point, right? Right? But probably not both, right? But what about light? Now, there had been this debate go back hundreds of years of what is light fundamentally? Is it fundamentally a wave or a particle? Isaac Newton thought light existed as particles, but von Huygens, some other scientists said, well, actually, if you take a card and you cut a couple slits in the card and you shine a light through, it'll create an interference pattern on the back wall. And we know that only waves does that, hence light must be a wave. So they thought they had that categorized, right? But if light's a wave, then you can keep increasing the frequency. And guys, if you increase the frequency, what's happening to the wavelength? It's getting less, right? So isn't it the higher the frequency, the shorter the wavelength, the speediest wavelength is frequency, right? So let's increase the frequency, hence decrease the wavelength, and there would be a larger and larger energy associated with that. Now, according to this graph, and I don't have the vertical axis exactly labeled, but you guys get the idea. Okay? You could fit more and more and more energy for higher frequencies, and it should follow this black curve right here, right? But if you go back to those ovens, like those black boxes, and you get empirical measurements, say also from the same temperature, so 5,000 Kelvin, this is the empirical data they actually got. It's on this blue curve, which is not nearly as much as classical theory would have predicted, especially for these higher frequencies, right? You change the temperature. I got a couple other temperature curves on here too, right? So lower temperature should be less energy. That kind of makes sense, right? But what's the mismatch here? Okay, so what could possibly explain that? Okay. Now, hold on to that idea because really on the journal that you guys have, I'm going to kick off with this question of like, how small are we talking about? Okay, so a couple of big things you'll see with quantum mechanics. One is this duality of particle and wave nature of matter, right? So we're going to hit that pretty soon with the photoelectric effect, right? But leading into that, the scale that we're talking about is maybe on the size of an atom, right? Okay, so when you get down to atomic scale, you get this ambiguity of do things exist as waves or particles, and also do things exist in discrete quantities or probabilistically. Okay, so like this, I'll show you guys my notes here in a minute. So you guys get out of this.
You probably already know that everything is made up of little tiny things called atoms. You might even know that each atom is made up of even smaller particles called protons, neutrons, and electrons. And you've probably heard that atoms are small. But I'll bet you haven't ever thought about how small atoms really are. Well, the answer is that they are really, really, really small. So you ask, just how small are atoms? Well, to understand this, let's ask this question. How many atoms are in a grapefruit? Well, let's assume that the grapefruit is made up of only nitrogen atoms, which isn't at all true, but there are nitrogen atoms in a grapefruit. Well, to help you visualize this, let's blow up each of the atoms to the size of a blueberry. And then how big would the grapefruit have to be? It would have to be the same size of, actually, the Earth. That's crazy. You mean to say that if I filled the Earth with blueberries, I would have the same number of nitrogen atoms as a grapefruit? That's right. So how big's the atom? That's really small. And you know what? It gets even more crazy. Let's now look inside of each atom. That's the blueberry, right? What do you see there? In the center of the atom is something called the nucleus, which contains protons and neutrons. And on the outside, you'd see electrons. So how big is the nucleus? Well, if atoms are like blueberries in the Earth, how big would the nucleus be? You might remember the old pictures of the atom from your science class, where you saw this tiny dot on the page with an arrow pointing to the nucleus. Well, those pictures, well, they're not drawn to scale, so they're kind of wrong. So how big is the nucleus? So if you popped open the blueberry and were searching for the nucleus, you know what? It would be invisible. It's too small to see. Okay, let's blow up the atom, the blueberry, to the size of a house. So imagine a ball that is as tall as a two-story house. Let's look for the nucleus in the center of the atom. And you know what? It would just barely be visible. So to get our minds wrapped around how big the nucleus is, we need to blow up the blueberry to the size of a football stadium. So imagine a ball the size of a football stadium, and right smack dab in the center of the atom, you would find the nucleus. And you could see it. And it would be the size of a small marble. And there's more. If I haven't blown your mind by now, let's consider the atom some more. It contains protons, neutrons, and electrons. The protons and neutrons live inside of the nucleus and contain almost all of the mass of the atom. Way on the edge are the electrons. So if an atom is like a ball the size of a football stadium, with the nucleus in the center and the electrons on the edge, what is in between the nucleus and the electrons? Surprisingly, the answer is empty space. That's right, empty. Between the nucleus and the electrons, there are vast regions of empty space. Now, technically, there are some electromagnetic fields, but in terms of stuff, matter, it is empty. Remember, this vast region of empty space is inside the blueberry, which is inside the Earth, which really are the atoms in the grapefruit. Okay, one more thing, if I can even get more bizarre. Since virtually all of the mass of an atom is in the nucleus, now there is some amount of mass in the electrons, but most of it is in the nucleus. How dense is the nucleus? Well, the answer is crazy. The density of a typical nucleus is 4 times 10 to the 17th kilogram per meter cubed. But that's hard to visualize. Okay, I'll put it in English units. 2.5 times 10 to the 16th pounds per cubic feet. Okay, that's still kind of hard to figure. Okay, here's what I want you to do. Make a box that is 1 foot by 1 foot by 1 foot. And let's go and grab all the nuclei from a typical car. Now, cars on average weigh 2 tons. How many cars' nuclei would you have to put into the box to have your 1 foot box have the same density of a nucleus? Is it 1 car? 2? How about 100? Nope, nope, and nope. The answer is much bigger. It is 6.2 billion. That is almost equal to the number of people in the Earth.
Ooh. All right, so it's pretty close to the end there. Wraps up a couple things. Right. So here's some things that I got out of that. Now, you got some interesting things. You can write whatever you like in any one of these quadrants. Again, I'll help you guys out. So here's what I would have written. If you want to write what I wrote, that's perfectly fine too. So how small are we talking about? He's saying if you look at the number of nitrogen atoms in a grapefruit, let's say it's just made all out of nitrogen, just to really simplify it, right? That'd be comparable to the number of blueberries that would take to fill the Earth. Say if you blew it up, if you scaled it up. So that's the proportion that we're talking about, the sense of scale we're talking about, the sense of scale, right? Of course, you could put a hard number on that, and like a metric units, so many meters, but it's a different picture, right? And then what about if you dive inside the structure of an atom? What does that look like? Now, this goes back to, I think a few days ago, I mentioned the Rutherford experiment. So scientist Ernest Rutherford was firing particles at gold foil. And most of those particles would just travel straight through, but sometimes they would bounce off and look erratically in different directions. And from this experiment, he was able to determine the model of the atom that you guys probably learned in past science classes, which is that there's this densely There's this dense nucleus that's positively charged, has the protons and later on neutrons. People found out, and there's this electron cloud that goes around the nucleus that has very little mass, relatively. Right? So, in terms of size, the nucleus to the atom, right? Here's a syllogism, is comparable to what a marble would be in a giant stadium. Right? Right? And then, since almost all the mass is in the nucleus, because proton, neutron have almost all the mass, and then electrons is tiny compared to that. Okay. The density of the nucleus would be like if you took 6 billion cars about and shoved them into a 1 cubic foot box, right? Which, by the way, would also not be dense enough even to create a black hole. A black hole is even more dense than that, but there you go. Right? You took all the mass, right? So almost. So what does that mean then? So almost all the, actually, sorry, all the matter that you guys are seeing right now in this room is almost all empty space, right? And really, the amount of mass is just concentrated mostly in that really dense nucleus right there. All right, so that's the scale we're talking about. All right, by the end of today, we'll come back and we'll revisit structure of an atom and what's going on with that electron field. Right, but need to make some connections in the meantime. So yeah, I was looking at the order of these topics here. I have different versions of this that I printed out over the years. We're gonna skip around a little bit. So just keep reordering this thing. Okay? Let's go to the photoelectric effect, right, which actually all these quadrants are going to tie together. Okay? So photoelectric effect.
So let's talk about the photoelectric effect. The photoelectric effect is a very important effect that was discovered by Heinrich Hertz in 1887, who was incidentally the first guy that made electromagnetic waves and was able to demonstrate their existence. It was during this study of electromagnetic waves that he saw that if you send ultraviolet light onto metals, you'll get sparks coming off. Now, he didn't really know what it was, but he was the first one to see that effect. Now, later on, it was explained by Albert Einstein in 1905. He actually won the Nobel Prize in Physics for that explanation later on. This explanation actually cemented the place that photons have in the development of quantum mechanics, because the photoelectric effect was one of the first direct observations of photons that can even be pointed to. All right, so what is the photoelectric effect? Well, essentially what we're going to do is we're going to take a freshly cut piece of metal and put it in a vacuum. And then we're going to shine light on it. Now, sometimes this light will cause electrons to jump off of the metal. All right? Now, classically, we would expect, light's a wave, right? So if you pump up the intensity, then you ought to get more electrons, right? So regardless of what the metal is, if I shine a 300-watt laser on it, I ought to get some electrons jumping off. So that's what I expect. The observation is that that's not what happens. All right? The observation is that if I have some frequencies, yes, increasing the intensity will increase the number of electrons. But if I try to go below a certain frequency, I don't get any electrons at all. Doesn't matter what the intensity is. Doesn't matter. And it's a sharp cutoff. Get electrons? No electrons. All right? So this was not understood at all. Now, the experimental setup is important to understand. What we're doing is we've got a vacuum chamber in here. We've got a circuit that we're driving by a battery. Now, this is all vacuum. Nobody can get across without an impetus to do so. The electrons, however, would desperately like to be on this side because that's the positive side. Remember, the long side is the positive side of the battery. So the electrons really do want to jump across. So what we do is we then shine our light. Now, if an electron is liberated, it's going to jump across, definitely, because it wants to be on that positive side. But the electrons are in the metal. They have to be liberated from the metal first. So, classically, we expect several things. We expect you increase the intensity, you're going to increase the electron. We also expect you increase the amount of time because it's a wave, so the electron should be absorbing the energy as time goes on. And you increase the amount of time, you should increase the amount of energy. That's not observed. So, how do we understand what's observed? Well, it turns out we need a little bit more in order to really do this. So what we're gonna do is we're gonna ask, how much energy do the electrons get when we shine this light on them? And the way we're gonna do that is we're going to reverse the battery. So now the electrons really don't want to make that jump. And in fact, they can't make that jump unless their energy is higher than the amount of energy it requires to jump from that side to that side.
All right, so he's leading up to this graph on the right side of the board. You guys see this energy versus frequency, and there's some threshold frequency where anything below that you get zero, and after that there's a direct relationship. Show you guys exactly what that looks like. Here's some actual data from a 1916 version of this experiment, and the first version of this happened back in 1887. Okay, so all right, so how much energy are we getting as a function of frequency? Now here's how the story goes. Suppose you have a solar panel and you're trying to collect energy on it, right? And you have, say a red light. You shine the red light on that solar panel. Well, red light, that could be like back over here before this threshold frequency. So, okay, so you get nothing. You say, okay, well, maybe I'll just make the light brighter. Now, according to classical mechanics, say like before 1887, they thought, well, if you just shine the light brighter, that should correspond to more energy, right? So maybe you should get, but empirically, you still get nothing. It doesn't matter how bright that red light would be. But if you change it from red to blue, we can cross this threshold frequency because blue has a higher frequency. Well, now you can get some energy, right? And now maybe if you shine it brighter, then you can get more energy. But anything before that threshold, nothing. Anything after that threshold, actually, if you increase the frequency, then you get proportionally more energy out of that. Okay? Now, what could possibly explain that? That experiment was sitting around since 1887 for a couple of decades before Einstein came along in 1905 and interpreted what that actually means. Right? So, for you guys up to speed here. Right, so we got photoelectric effect. So look at this graph. Energy as a function of frequency. Right? And you guys just saw that graph. You guys saw the data. So yeah, it looks something about like this, where there's this threshold frequency here. Right? Anything below that, you get nothing. Right? Anything after that, it's a direct relationship. Actually, the slope of this line oftentimes is called H. It's called Planck's constant. It's like per photon, right? Planck's constant. Direct relationship, right? Right. No, this is where Einstein was looking at this again, been sitting around for about a couple of decades. And in 1905 said, I have an interpretation. I think what this means is that light not only has wave properties, but what I'm about to show you guys is also has particle properties. And so it has a dual wave particle nature. And so it's particle properties in addition to wave properties. Right? This is what Einstein actually won his Nobel Prize in physics for. Right? Like nowadays, we mostly know Einstein for theory of relativity. Right? But weirdly enough, yeah, he actually won the Nobel Prize for the interpretation of this photoelectric effect. Right here, it says light has a dual wave particle nature. Wave particle nature, right? Because people have known for a long time that okay, light has a wave nature. You know that from say a double slit experiment, right, with a interference pattern. Okay? But now, why did Einstein think that this also shows a particle nature of light in addition to the wave nature? Okay, so I give you guys an equation here. So here's my poster version of this photoelectric effect. Right? You guys see E equals HF, and then minus the side here. It's called the work function because this could have an intercept, right? But that intercept aside, because well, I mean, you kind of get down to 0 hertz frequency, right? Is mostly maybe you care about this direct relationship post threshold frequency. I'll call that E equals HF. Right? So, right. So you guys see up here, quadrant number 2, you got E equals HF. Right. I'm gonna modify this. Might modify this in the future. I'm gonna give you guys a garden hose analogy. Okay, so here's how Einstein was thinking about this photoelectric effect. Okay, so draw a couple of garden hoses. Hose. Okay, and let's say we're rolling marbles down these hoses. Right, rolling marbles down. Okay, that we're rolling them down differently. On one of these, I'm going to have a low frequency of rolling marbles, and this one is going to be a high frequency. ooh, that could kind of correspond to a low frequency light wave or a high frequency light wave, right? Okay. And low frequency means, well, maybe you roll a marble, oh, I don't know, like every second. So bloop, 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 bloop. Okay, got a bunch of marbles going down. Okay. Now, those marbles, those are discrete particles, definitely, right? Okay. But remember, making some kind of connection to waves here. So drew them kind of in a wave pattern, so you can kind of see a sort of a wave emerge out of that, right? Okay, so low frequency, right? But what if instead of 1 per second, what if you just roll a bunch of marbles like down this garden hose, and that V correspond kind of to a high frequency? It'd be kind of like this, wouldn't it? Hey, just be a bunch of marbles and take them in a wave pattern. Just to remind you guys that light is also a wave. It's not just particles, but it's also wave, right? So, ooh, that could correspond maybe to a high frequency wave, right? So, the low frequency might be like a red color, and the high frequency might be like a blue color, right? Well, these marbles, call these marbles in the analogy, right? Are kind of analogous to what Einstein called photons, which could be particles of light. Okay. And that would explain this photoelectric effect. Because if you roll down twice as many marbles with twice the frequency, okay, and every marble represents, say, a packet of energy, well, twice the frequency could correspond to twice the energy that you're rolling through. Get that? Okay. I forget if I mentioned it this all day, but Isaac Newton actually thought that light was made out of particles, right? And then light was shown, of course, to have these wave properties with interference patterns. And then Einstein's back saying, actually, you know what? Light does have this particle nature after all. So it's actually both. We got this dual nature. Okay. Now let's look at this Planck's constant right here. What is this Planck's constant? What is the slope of this graph? Okay, so to tag a number to it, it goes 6.626. So we're calling it H. So say H equals, for Planck's constant, H equals 6.626 times 10 to the negative 34. And then what we've got here, some kind of energy per frequency. So it could be joules per hertz, but oftentimes that's just called joule seconds, because you guys know hertz is 1/seconds, right? Okay. Because 10 to the minus 34. I don't know if you've ever seen a number that small in your entire life. So definitely not in this class up to this point, right? 10 to the minus 34. Isn't that like 0.00000? It's like a string of zeros before you get to 666. Okay. So that's to say like a shallow slope on this graph, right? Like how much energy is contained within a single photon? You can think of it that way. Okay. That's that ratio. That's the slope of that graph right there. Okay. Okay. Now, what about Planck time and Planck length? What do those refer to? Okay. Say you're looking at the universe. Looks like it's all fluid and continuous, right? At least classical physics would say so. I mean, all the equations we've done since August, assume that you can always subdivide a length in half and half and half and keep going down, right? But what if you're watching a video on your phone screen? Yeah, okay, it also looks fluid, looks like the real world, right? But if you zoom down far enough, say you're an ant crawling across the phone screen, wouldn't you actually see a bunch of pixels just lighten up, right? And that's sort of the video becomes quantized frame by frame and pixel by pixel, right? So go back to the universe. Could the universe be somewhat quantized? And that's the idea of Planck length.
What is the smallest distance you can think of? If you're thinking of something like the width of an atom or electron, then you are way off the mark. There is a distance so unimaginably small that it makes distances comparable to an atom seem giant. This distance is referred to as the Planck length. The Planck length is roughly 1.616 times 10 to the negative 35th meters long. However, numbers to such an extreme value such as this are very difficult to comprehend. So let's put it into perspective. The approximate smallest distance an unaided human eye can observe is about 0.1 millimeters. This is about the width of a single human hair. Now, imagine expanding this distance to the size of the observable universe. How big would a Planck length be? Coincidentally, a Planck length would now be 0.1 millimeters long. In other words, the width of a human hair is just as close in size to the observable universe than it is to a Planck length. The question that arises here is, why is that the smallest distance? Why can't we take measurements that deal with half a Planck length or a quarter of a Planck length? Although this concept works out well in mathematics, in the real world, things are much trickier. At the Planck length, ordinary space and time cease to exist. There's possibly just nothing in between two individual Planck lengths.
right, so yeah, we get to quantum mechanics. That's what quantum also means, right? The universe becomes quantized. So is the universe in a sense pixelated? Yeah. Okay. In space, that's what Planck length is. Right? But also in time, if you take the Planck length and divide by the speed of light, because you guys know speed of light, well, that's also limiting speed. Right? There's also a quantized amount of time. Right? So what's the smallest unit of time that makes sense to talk about? And it works out to this number. So we got 10 to the minus 35 meters here. We got 10 to the minus 44 seconds here. Okay? Now, you saying Planck length, if you go from Planck length to a human hair, that ratio is the same as width of a human hair to the width of the observable universe, right? Again, since the scale. Okay. What about Planck time? Like, what is 10 to the minus 44 seconds? Right? What does that mean? Well, let's do a quick calculation here. How many seconds have there been since the beginning? Right? Is the universe about 14 billion years old? About? Right? I'll call it 14 times 10 to the 9. So like 13.8, whatever, rounding a little bit. Right? Okay. Now, how many seconds is that? Well, if this is how many years, and I'll go through Earth time to get the seconds. I know there's about 365 days in a year, 24 hours in a day, 3,600 seconds in an hour. So, and really, I just care about order of magnitude at this point. So, is that 10 to the 17 seconds? Right. So, since the Big Bang, how many seconds have there been like in the universe? 10 to the 17, let's call it. Right. How many Planck time units are there in a single second? Wouldn't that be 10 to the 44? Ooh, so there are way more Planck time in a single second than there are seconds that have ever existed in a sense of scale. So we're talking about like crazy, crazy small here. All right, so you guys good on, we're starting to quantize the universe here. The light, which we had known for a long time, exists in waves. Einstein comes along in 1905, says, actually, you know what, that Heinrich Hertz photoelectric effect we're looking from 1887, actually that does show that light also exists as particles. We got these packets of energy I'm calling photons now, right? And now we're going to get to de Broglie, who says, I wonder, does this duality exist for other things too, not just light? And what could that possibly explain?
Photoelectric effect not only confirmed Planck's theory, it showed directly that bundles of energy already exist in the electromagnetic field. In other words, light comes in particles which are now called photons. But wait a minute. A century earlier, Thomas Young had proved light travels in waves. Was it now going to turn out that light is really made of particles after all? Perhaps this whole business of particles and waves was in need of an entirely fresh perspective. Louis de Broglie got a history degree en route to a career in French government, a fresh approach to physics if there ever was one. Maybe that's why, in the 1920s, he was the one to ask a crucial question. If light waves can be particles, is it possible that particles, such as electrons, can also be waves? To begin with, particles have energy and momentum, while waves have frequency and wavelength. Obviously, these entities have different kinds of properties, but de Broglie suspected there was some sort of connection. And Planck's theory had given a clue to what it might be. Max Planck had associated the energy of a light particle with the frequency of its wave. Going a step further, de Broglie combined this with the particle's energy according to Einstein's relativity theory. E equals mc squared. This bold mixture of wave and particle properties suggested the next step. Good particles traveling at less than the speed of light had their momentum related to their wavelength. De Broglie believed so. He thought that just as a particle's energy is related to a frequency, a particle's momentum is related to a wavelength. It was a radical idea. Not only can light waves behave like particles, but particles can behave like waves.
Ooh. Okay, so now we got an extension of this wave particle duality to other types of matter too. And so back in this day, these formulas were floating around. We got E equals mc squared. There's your mass energy equivalence from about 1905. Right? You got speed is wavelength times frequency for waves. Right? That had been around for a long time. Right? And now enters quantum mechanics. We get a lot like photoelectric effect. Right? Energy is Planck's constant times frequency. Right? So now he starts mixing and matching these formulas and says, well, what can I figure out about maybe any kind of matter, right? And it comes up with, actually, you can describe a wavelength of any particle, right? So wavelength would be take Planck's constant, which is an already tiny number, it's 10 to the minus 34, right? And divide by the momentum of that particle. Now, for ordinary size objects like this right here, if you take 10 to the minus 34 and divide by the momentum of this, right, you're going to get something that so small that you wouldn't be able to measure it. Right? But what if the mass you're talking about is a tiny mass? Like, ooh, how about an electron? Do you think that an electron would have such a small mass and therefore such a small momentum that it would have a discernible enough wavelength that would actually matter to the material property? Yeah, right. And that is lead to we're going to do one more of these today. So I'm going to get to number 6 today. At least to energy levels and electron waves. Do you guys remember from chemistry electron configuration? All right. Where's my electron? Here's electron configuration. And so I got a couple of these for you guys, right? One goes like this, so as energy goes up. If you guys remember, this 1s box can carry 2 electrons, so that can cover hydrogen and helium. But then we get to lithium and beryllium, the energy level for the 3rd and 4th electrons jumps way up, and so on. So electrons can only fit at discrete orbits. Now, why would that be? And this goes on to explain all of chemistry. So the entire class of chemistry took on all those chemical reactions, okay, is really just an offshoot of this. Okay? But why? If you take the analogy of electrons going around the nucleus, is kind of like planets going around the star in a solar system. Well, that analogy is not perfect because one reason is that planets can kind of be any distance from their parent star, right? But that's not true for electrons. Right. And I have another perspective on this, but I think this file is like half corrupted or something. I don't know what's wrong with this. Right? You guys maybe see this version, maybe in a chemistry textbook too. Right? It's a different perspective on the same idea. I'll draw you guys a better version of that. Right? So let's bring in Paul Hewitt here. Explain this.
If you think of the electron as being like a wave, here's a nucleus here. It's like a wave. Here's an electron that doesn't make it. At that particular level, the electron's going to cancel itself if it's a wave, maybe a little higher up. And I'm just roughing this off and hoping, well, let's suppose I went like that. See if it can close in on itself, then that wave is permitted. And you will have an atom that has an electron that resides at that particular level. And then the next level out is one more wavelength. And one more wavelength. It's like if you made a necklace made out of paper clips. You get a certain circumference. And the next circumference you can get is increased by one more paperclip. See what I mean? Then another one. And you couldn't make a paperclip in between in terms of the radius when it's spread out into the circle if you have discrete numbers of waves. And this was a mystery for a long time. Why is it that the atoms, the electrons only exist at certain levels? See? It didn't make sense with a particle view. But if you look at the electron as a wave, you can say, hey, it does make sense. It can exist at 1 wavelength, 2 wavelengths circumference, 3 wavelengths circumference, 4 wavelengths circumference, and every one of those has its own discrete radius.
All right, so here you got the electron configuration marked up here. Got an upside down version of that one. All right, so these suborbitals, we got the S, the P, the D, the F, right? And the electrons fill in always a certain order. It goes 1s, then 2s, then 2p, and 3s. Remember, each one of these can hold 2 electrons. Okay, so as they're going up, right? Here's a diagram, just follow these diagonals, tells you the order, right? So if you get up to like gold, right, now it's a more complex electron configuration, but it's always in that order, and electrons can only fill certain orbital spaces, okay? And here, I'll draw what Paul Hewitt had. You got some nucleus of an atom right here, some nucleus, okay? And say some electron in orbit, like attached to that nucleus, okay? But to complete one of these orbits, right, if electron has these wave properties, you have to complete some whole number of wavelengths to go around. Okay? Now, if you look at the actual orbital shapes of electrons and electron fields, it's more complex than that. You can see them in 3 dimensions. Okay? This is really just a simplified 2-dimensional model, but you guys can get the idea from that. Right? Okay, so the fact that electrons have these wave properties, right, leads to this electron configuration and all of chemistry. And where we're going to pick up either Monday or Tuesday is how that can actually explain, one of many things here. Right? Why is glass transparent? Why is air transparent? Why is anything that is transparent? And why are some things not? Okay? That can be explained by this too. What's the interaction between, say, that glass window and light? Why does visible light go through that glass window? All right, so that's our pause point today. You guys know our main focus on Monday is we're gonna go back to the final exam review and then alternate back and forth. All right, you guys have a good weekend.